So far in our exponential and logarithmic unit, we have graphed exponentials and logarithms. We have discovered and worked with some properties of logarithms. And now we're ready to solve some equations. We're going to start by solving exponential equations, and then the next lesson will be solving logarithmic equations. But the steps are really pretty simple. We're going to isolate first the exponential expression, which means we want either b to the x by itself on the right-hand side or the left-hand side of the equal sign. So as much as we can isolate it, we're going to isolate it. Then we're going to take the natural log of both sides. So put ln of both sides. Then we're going to apply the power rule or identity. Remember, this means that we can simplify any exponent from our argument as the scalar multiplied in front of the logarithm. Or if you have a base of the logarithm and a base of whatever's the argument, you can basically cancel them out and it's just the exponent, which those are truly the same rule because power property would bring it back to the front, it'd be the scalar, all that stuff. And then you're going to solve for x, but I'm going to put a little note here that do not compute, so don't type anything into your calculator until you have finished algebraically solving for x at the very end, because we're going to have to round these numbers and I don't want us to lose any value if we round too early. So we should be algebraically rearranging these equations until we have x equals something, and then we can plug them into our calculators. Okay, so if we look at this first one, step one said to isolate. Well, guess what? The exponential expression is already isolated. Great. So the next step is to take the natural log of both sides. So natural log of 6 to the x, and the natural log of 42. Well, that power property tells me that the x can now be a scalar or multiplied in front of the natural log of 6 equal to the natural log of 42. And if you think about it, natural log of 6 is a number, the same way natural log of 42 is some number. So what I have right now, and don't write this part down, is I really have an equation like 5x equal to 10. And how would we solve a scalar times x equal to some number? Yeah, we would just divide. So 10 would be equal to 10, x would be equal to 10 divided by 5, which is 2. So we're going to do the same thing with these natural logarithms. Okay, let me erase this for a second. We're treating this as if it's a regular linear or in some cases quadratic expression, and we're solving for x. So I'm going to divide by natural log of 6 on both sides. So I'd get the natural log of 42 divided by the natural log of 6. And at this point, this is something you can throw into your calculator. The natural log button is on the left side. It's ln. It's like the third button from the bottom. But you're going to just literally make a fraction and say natural log of 42 divided by a natural log of 6. And I know I can't really show you how to type that in, but you guys can listen to instructions. You'd get x is approximately 2.086. We're going to round to the nearest 3 decimals. Now, one thing we want to be able to do is check our work on these problems, and this is the only problem I'm going to show you this on, so make sure you understand it. There's a button you've probably never noticed on your calculator. It's second from the bottom. It says STO with like a little arrow right here, and that means I'm going to store a number. So what I like to do is when I get one of these values like an approximation, and I want to check and make sure my answer works, I'm going to store that value in the calculator. So what you're going to do is you're going to have, we just pressed enter, so the last thing on your calculator should be 2.086 with a whole bunch of decimals behind it. And you're just going to press that STO button and store it as some letter. I always like to pick the letter K because that's what my first name starts with, and I'm just a little bit vain. So I'm going to store it as K. And now to check my work, the same way you would just plug in the number in a linear equation to check your work, if you type in 6 to the, and then just that number or letter K that you stored it as in your calculator and press enter, it's going to give you 42. And if it doesn't, you didn't get this right. So you can still plug in your answer choice. It's a solution, and you can still plug in that solution for the value of x to see if it comes out to what you want. You can always check your work. Now again, that's storing the value. The reason that we do that is because our answer is an approximation and we want to make sure we plug in the entire number. So store the value as one of the letters and then raise 6 to whatever that letter is. It should give you 42. If you need me to go over this with you live, just come ask me and I will show you. For letter B, this time we are going to have to isolate the exponential expression. This is the exponential expression here, and it's not by itself yet. So just as if this was a linear equation, I'm going to add 3 to both sides. So now it would say 5 to the x plus 1 equal to 24. And my exponential expression, though the exponent itself is complicated, the base and the power are by themselves. So I'm going to take the natural log of both sides. And then use that power property to realize that x plus 1 can now be the scalar in front, okay? And I lost a lot of people on this part earlier. And so we really just need to remember our inverse operations. Right now, the quantity x plus 1 is multiplied by natural log of 5. And this is just a number. It's a coefficient of this parentheses. It's as if it could be distributed inside, which we really could do, but we could also divide both sides by natural log of 5. Because then we have the natural log of 24 divided by the natural log of 5 is equal to x plus 1. And we know how to solve for x here. That's going to be natural log of 24 divided by natural log of 5, all minus 1. Again, remember, we wait to the very end to press enter on our calculator. I recommend using the fancy fraction on this if you're not 1000% sure that you know how to use parentheses appropriately on your calculators. But this would be x approximately 0.975. And again, you know how to check it. You would just store this as some value. I like k because that's my initial, and plug it back into the equation here to see if you get 21. Question C here, again, we're just going to follow the steps. It says to isolate the exponential expression. The base and the power are by themselves, so I can take the natural log of both sides. That would be the natural log of e to the 3x equal to the natural log of 8. Hopefully you notice the natural log of e is that identity property. They cancel out. This is now just going to be 3x equal to natural log of 8. And solve for x. So you divide by 3 on both sides. The natural log of 8 divided by 3. And once we have that, we can throw that into a calculator, and we would get approximately 0.693 when we round. And again, quickly check your work by storing that rounded value or the unrounded value from your calculator as some letter and plugging it into the original equation to see if it gives you 8. And it would. All right, let's try D here. Is the exponential expression isolated? No, this is the exponential expression right there. The base is e. E is the only part of this that has an exponent attached to it. It's as if I need to isolate 3x minus 1 equal to 12. I just want the x isolated. So I'm going to add 1 to both sides. So it'd be 3e to the 2x equal to 13. Divide by 3 on both sides. E to the 2x equal to 13 divided by 3. Now my exponential expression is isolated, and I can take the natural log of both sides. Identity property allows me to know that this is really just 2x equal to the natural log of 13 divided by 3. And if we quickly solve for x, we're going to have the natural log of 13 divided by 3, all divided by 2. And that's when you start throwing it in a calculator, you'd get approximately 0.733. Checking your answer by storing that value in the calculator for some letter and plugging it back in. All right, E and F are where it gets crazy. We're going to use some mad algebra skills here. I love these problems. I think they're super fun. What you might notice is that there are 2 exponential expressions here. This is about as isolated as it can get. Okay, the bases are by themselves, but we really can't simplify this anymore. So we are going to just take the natural log of both sides. So we'd have natural log of 4 times 2 plus to the 2x plus 3, equal to the natural log of 5 to the x. On both sides, I can use the power rule to bring that exponent forward. So 2x plus 3 times the natural log of 4 equal to, and I'm going to put this in parentheses on purpose, x times the natural log of 5. Okay, when we're solving an equation for x, we need to get all the terms with x on one side. This, if we think about it as a linear equation, would be 2x plus 3 times some number, I'm going to use 10, equal to x times some number, I'm going to use 12. Okay, hopefully you'd think, oh, well, I'm going to need to distribute that 10 inside this parentheses so that I can get the x out of the parentheses, start moving things around where the x's are all on one side and I can combine them together. And if you're thinking that, you're on the right track. So we are going to distribute that natural log of 4 to both things inside this parentheses. We're going to end up with 2x times the natural log of 4 plus 3 times the natural log of 4 equal to x times the natural log of 5. There are two terms up here that have an x attached to them. This term has an x, and this term has an x. This one does not, so it's like my constant. It is a constant, it's just an ugly constant because we can't make it a cute fraction or a whole number. So when I'm solving regular equations, I want all the terms with x's to come onto the left-hand side and all the constants to go to the right-hand side. So that's easy, that's just adding and subtracting. 2x times the natural log of 4, I'm going to subtract x times the natural log of 5 to the left-hand side and subtract 3 natural log of 4 to the right-hand side. So inverse operations. If you notice now that both of these terms have an x in them, so I'm going to divide that x out. It's called factoring out a value, what they have in common, and what's left over is 2 times the natural log of 4 minus natural log of 5. That's factoring out a common term. We did this when we did inverse functions, so we factored something out. And at this point, I just want that x by itself, and all of this right here is really just a number, like as if this equation said 10x equal to negative 5. And what would we do to solve for x? We'd just divide by that coefficient, which is that large expression right there. So we're going to take the negative 3 times the natural log of 4 and divide it all by 2 times the natural log of 4 minus the natural log of 5. Type all of that into your calculator at the same time. Don't do anything before. One enter, basically. And we're going to get negative 3.576. And then, because we're good students, we're going to store it in our calculator, and we're going to check our work and make sure both sides are equal. F kind of follows, it's similar in the way that we solve it, because when we start, both sides are already isolated. Both of the bases with their powers are as isolated as we can get them, so we just start by taking the natural log of both sides, natural log of 3 to the 2x plus 1 power, equal to the natural log of 6 to the x plus 2 power. Move both of those exponents using the power rule in front of the now scalar natural log of 3. Sorry, I didn't change colors. Equal to x plus 2 times the natural log of 6. Both sides have parentheses, and if you're solving linear equations, when you have parentheses with a number in front of it, you multiply using distribution. So we're going to do that. We'd end up with 2x times the natural log of 3 plus the natural log of 3 equal to x times the natural log of 6 plus 2 times the natural log of 6. I just multiplied by those scalars, by those coefficients. There just happen to be natural log of 3 and natural log of 6. All of the terms with x's I want on the left-hand side. This term has an x and this term has an x, so I'm going to move them to the same side. 2x times the natural log of 3, and I'm going to subtract x natural log of 6 onto the left-hand side. And then the two terms without an x should be on the right-hand side. So I'm going to subtract the natural log of 3 over there. Inverse operations. Again, hopefully you notice that we still have those common x's over here that we can factor out. This is going to be x with the leftovers of 2 times the natural log of 3 minus natural log of 6. And then to solve for x, I just divide by the constant near it, or by the coefficient near it, which means x is going to be 2 times the natural log of 6 minus natural log of 3, all divided by 2 natural log of 3 minus natural log of 6. And again, don't press enter until you have it all solved for x, because then you just type one thing in your calculator and you'd get that x is approximately 6.129. Check that value by storing it for the letter x or for any letter in your calculator, and evaluating both the left-hand side and the right-hand side of the original equation to make sure they come out equal. G here, I like this question G because it's really interesting. At first glance, hopefully you say, okay, first of all, it is not isolated, like the exponential expressions are not isolated. Also, there's two of them with different powers. And if you remember back to our exponent rules, we cannot combine these two things because they have different powers. There's no really way to combine them unless you notice that these are essentially x squared minus 4x plus 3, right? Let's just let x be e to the x. You see how this is actually just a simple quadratic where the base is not x, the base is the function e to the x. It's called quadratic form. We'll write that down. Quadratic form. When other equations take on a quadratic form, you can treat them as if they are a quadratic using whatever form of equation they gave you. So the way that we solved quadratics is by factoring them, because we can't isolate the exponential expression, but we can get there eventually if we treat it like it's a quadratic. The base is e to the x, so instead of putting x's in both parentheses, I'm going to put e to the x's in both parentheses. I want a number that multiplies to 3 and would add to negative 4. Well, the only things that multiply to 3 are 3 and 1, so I really hope that works. And the only way to get a negative b value and a positive c value is if both of the factors are negative. The zero product property that we've been using since like day 1 is going to allow me to do e to the x minus 1 equal to 0 and e to the x minus 3 equal to 0. Now I have tiny little exponential equations that I can isolate. I want to get these e to the x's, the base and power by themselves. So plus 1 and plus 3. Now they're isolated. I can take the natural log of both sides. And the product property on both of them, not product property, sorry, identity property on both of them, we'd get that x is approximately, or x is exactly 0, because natural log of 1 is 0, and that x is approximately 1.099. I have two values for x. I can check both of them in the original equation, store both values. I mean, you don't have to store 0. It's just 0. And to make sure that the quadratic form of this exponential equation does come out to 0. Now, on the following pages, they're just screenshots essentially of the work for word problems. Really what happens with word problems, you just need to know what they gave you and where to plug it into the exponential equation that they gave you so that you can then solve it. So look through the work, make sure you copy down all of the work, and if you have questions about those applications, please let me know.